So today we're going to talk about complex numbers. So complex numbers are a set of numbers which include the numbers in the complex plane. So we'll get a bit more into what the complex plane is, but these numbers can be written in the form of z equals a plus bi, where a is the real part of the number, so it can be any number, 1, 2, 3, fractions, anything like that, and b is the imaginary part of the number z. Again, it can be any number. And in this case, I represents the square root of -1. So in traditional math, we cannot take the square root of -1, which is why we come up with this imaginary number, this fundamental imaginary number I, which is the square root of -1. And this is what b is multiplying. So all positive powers of I are 1, -1, I, or -I. So we can see that below, and you can write that out too if you want. So I to the 1 is just I, obviously. I squared is -1 because you take the square root away. I to the 3 is -I because that would be equal to -1 times I. And I to the 4 is simply 1, which would be equal to -1 times -1. And you can work that out yourself if you want to see in more detail. An important concept is the complex conjugate. So if z equals a plus bi, then z bar, or the complex conjugate of z, is a minus bi. So then there are a few things that we can do. So z times its complex conjugate is simply the a squared plus b squared, so it will be a real number made up of the square of the real part plus the square of the imaginary part. Z plus the complex conjugate of z is 2a, z minus the complex conjugate of z is 2b, and the complex conjugate twice of z is equal to just z. And again, these are things that you can work out on your own if you'd like to see them in a bit more detail. So we can express complex numbers in a form called polar form. So if we think of a complex number, we can equate it to a coordinate on the complex plane. The complex plane is where one axis is a two-dimensional plane where one axis is the real axis and the perpendicular axis is the imaginary axis. Generally, x is the real and y is the imaginary. So in the polar form, that means that it would be z equals x plus iy, or yi, it doesn't matter. And z equals the modulus of z cos theta plus I sine theta, where the modulus of z is simply x squared plus y squared, all square rooted, which is essentially the length of the position vector to the point, and theta is arctan imaginary over real. So you can visualize that. Note that the argument is not unique and it recurs in multiples of 2 pi, so just like any other Cartesian coordinate, if you go 2 pi around the plane, then it will be the same argument theta. So to multiply, simply multiply the moduli and add the arguments. Divide the moduli and subtract the arguments. For exponential n times, the modulus to the power n, and then multiply the argument by n. So that is how you do those operations with polar form. So we can also write any complex number in terms of an exponent, which is where we use Eulers formula. And this would be, so if z is equal to x plus yi, then it's also equal to, as we went over before, modulus of z times cos theta plus I sine theta, which is equal to modulus of z e to the I theta. So this is just another way to write it. And then an important note is that e to the I theta, the modulus of that, is equal to 1 for any angle. So without the modulus, it lies within the unit circle, and the modulus extends that that position vector. Another important thing, if z equals x, this is Eulers formula. So if z equals x plus yi, this equals r cos theta plus I sine theta, where r is the modulus of z, so it's the length of that position vector. Then this equals r e to the I theta. Then z to the n is equal to, as we went over, r to the n cos n theta plus I sine n theta. And then to translate this into the exponential form, all we do is multiply or take r to the nth power and then multiply the theta by the argument by n. Multiplying and dividing. So if you have it in algebraic form or rectangular form, which is z equals a plus bi, then we want to multiply the real parts. So a times a, multiply the imaginary parts, and then negate. So b times b, then minus. This happens because if you have bi times bi, this would be equal to b root negative 1 times b root negative 1. So this would be b squared negative 1. So just negative b squared, and then multiply the rest out. So it's similar. You can use the FOIL technique or whatever you use for any binomials, because it's fairly similar to a binomial. Just remember that to negate that I, because I represents the square root of negative 1. And then divide, we have to use a bit of a different approach. So we want to multiply by the conjugate of the denominator over the conjugate of the denominator. So the conjugate, again, being that z bar. For powers of I, we want to divide the power by 4, and then the remainder can act as the power. That's the same as, if you go back a few slides, then you'll see that that I to the power runs in cycles of 4. So then you can predict what it will be. We can find the nth root of complex numbers. So if there's a complex number a and it equals in exponential form re to the I theta, and n is a positive number, then z to the n equals a has n distinct solutions. And you can see that there. So essentially it's taking that 2 pi concept where the argument will be the same if you go 2 pi times a multiple of 2 pi times around, and expanding that. And the interesting thing about that is if you look at k, so if you look at that second expression, root n r times cos pi over n plus k 2 pi over n plus I sine, not pi over n, theta over n. So starting again, n root r times cos theta over n plus k 2 pi over n plus I sine theta over n plus k 2 pi over n. K is equal to any integer from 0 to the integer n minus 1, so 1 less than whatever n is. All solutions would be on the unit circle with radius r to the nth root. There are also roots of unity. So w to the n is the root of unity if w to the n is equal to 1. And the nth roots of unity are given by distinct numbers. And you can delve further into it using different constants and such, but we won't go too much into that today. So just for some examples, we're going to go over converting to polar form and then multiplying with polar form, converting to exponential form from rectangular, and then also dividing in rectangular form. And then for the extra example, which you can find in the description below, we're going to do a root question. So all solutions of that equation there. But first we'll do this. So sorry, let me just pull up the question here. Apologies for the delay. All right. So let's get started. So with number 1, we want to convert this 2 plus 3i to polar form. So we want to find z first. So z equals root a squared plus b squared equals root x squared plus y squared, where this would be a, and this would be b, or that would also be x, and this would be y, if you're thinking about it in traditional Cartesian notation and a traditional Cartesian plane. So then this would simply be root 2 squared plus 3 squared equals root 4 plus 9 equals root 13. All right, so we found z, and now we want to find theta. So remember, theta equals tan -1 or arctan of the imaginary over real. So I'll write imaginary over real, which is equal to, in the coordinates that we've used up there, tan -1 or arctan b over a. Okay. So then theta would be equal to tan -1 inverse tan of 3 over 2. And just putting that into a calculator. That is, and I'll keep it in degrees, but you could do it in radians as well. That is 56 degrees. So then all we have to do is plug it into the polar form. So then we have z equals root 13 times cosine 56 degrees plus I sine 56 degrees. Oops. And that is the conversion from algebraic to polar. So then for our second question, we want to multiply, so I'll just write it out, 4 cos 50 degrees plus I sine 50 degrees. See if I have enough room here. 5 cos 75 degrees plus I sine 75 degrees. So what we want to do here is we want to multiply the moduli rather. So I'll take these down here. I'll say 4 times 5 equals 20, of course. And so we'll just write the modulus z equals that. And then we want to add the arguments. So do this in a different color. Say 50 plus that 75. 50 degrees plus, sorry, I should write theta equals 50 degrees plus 75 degrees equals 125 degrees. So then we simply get z equals 20 cos 120 degrees plus I sine 120 degrees. And that is that. All right. So then moving on to our third problem, we want to convert into exponential form 5 minus 2i. So for exponential form, we need z and we need theta. So z is equal to root a squared plus b squared. And again, a and b are there. So then z would be equal to 5 squared plus 2 squared. I should say negative 2 squared, which is equal to 25 plus 4, which is equal to root 29. And then theta, as we said before, is equal to arctan of b over a, which is equal to arctan negative 2 over 5, which is equal to, and again, you want to be doing this on the calculator probably. So that spits out a number negative 21 degrees, which is also equal to 338 degrees. So then we can write it in that exponential form. Z equals Z EI theta. So then, which is equal to root 29 EI 338 degrees. And that is how you convert to exponential. Okay, finally, we want to do a division. So we have 2 plus 3i divided by 5 minus 2i. And remember what we want to do here is we want to multiply by the conjugate of the denominator over the conjugate of the denominator. So, so we'll say times 5 plus 2i over 5 plus 2i. So I'll kind of write this out longhand. So this is equal to 2 times 5 minus 3 times 2. Again, the minus because that is the imaginary parts multiplied. And then we can multiply the imaginary and the real parts. So plus 2 times 2i plus 3i times 5. And then, as we said before, the conjugate rule. So go back here. So with the complex conjugates, we'll just have a squared plus b squared. So it's really similar to if you had a difference of squares in a binomial in algebra. So this would just be 5 squared minus 4, that would be plus 4 squared Again, because those i's would, just a little note here, I times I equals -1. Let's put that in a box so that we remember it. So then this would be 10 minus 6 plus 4i plus 15i over 25 plus 16, which is equal to 4 plus 19i all over 41, if I did my math correctly. Yes. Okay, that is all for today. So if you, again, go into the description and find this completed example with some annotation, as well as the extra example. And thank you to Google Keep and Loom, and as well as my professors. And hope to see you again soon.